Let's see the system design with resistive as well as some sort of back EMF type or battery type load. So this is called a RE load. So in the single phase half wave rectifier, so this is our main source supply. So this source supply is connected to a breaker with the help of a diode, and that is given to a resistive load with a back EMF E, or maybe a battery voltage. So this battery voltage, say for example 10 volts, this resistance may be anything. So this is say Vs, say 100 peak of sine of omega t, and all these things are there. So let it be resistance value maybe 10 ohms or something, like whatever it is. So assuming the diode drop is equal to 0, then what is actually going to happen? Let us observe. So again, what we do, will draw. Again, I am representing this axis as time in seconds. This is the source voltage Vs. Now the source voltage is changing with respect to the time, and hence it will be like this. Okay, so this is Vs is equal to Vm sine of omega t. Now in this one the battery voltage is also there. Say this is the battery voltage that I am picking up. So now if you take this particular part into zoom, if you take this particular part into zoom, then we'll see this is something like this. This is 0, this is pi, in between pi by 2, in between there is a line here. This is the back EMF line. This back EMF line voltage is E. So let me assume this is at an angle of theta 1. So if this is pi, this may be at an value of pi minus theta 1. Okay, because it's a equidistance. Now, so till this point, till this theta 1 point, the voltage of the source is less than the voltage of back EMF. So that means this is more compared to this, and hence this diode is not in conduction mode until this theta 1 is reaching. So that means what? When this Vm sine of omega t or theta 1, sine of theta 1 is equal to E, that means this theta 1 is equal to theta 1. So this is equal to sine inverse of E by Vm. So till this point, till this particular point, the diode will not conduct. After this point only the diode starts conducting, but the diode starts conducting till this point only. What is this point? Pi minus theta 1. So now if I see my current waveform, how the current waveform is looking like. So now if I extend my lines here, so it will be 0, and then it will be current, it is going, and then it will be 0. So this value is theta 1, this is pi minus theta 1. Now at this stage, what is the voltage waveform across the diode? So this time the voltage is this voltage, so minus E will be appeared till this point. Then from here to here it is 0, but from here to here, so this voltage plus E, so that is how much? Minus E plus Vm voltage will be applied here. So let me assume this is minus E and this is Vm. this much amount of voltage will be appeared across this thing. So this is how we can notify this RE load. Now how much amount of current that is flowing through this one is can we find out? How, that is easily that say this is the current that is flowing through this part. So this current I is equal to, that is like Vm sine omega t minus E divided by R. Or you can put a KVL. So source voltage is equal to voltage drop across this. Source voltage is Vs is equal to VR is equal to I into R plus E. Now we need to find out I. Vs minus E by R is equal to I. Vs is equal to what? Vm sin omega t. So that is what I have written. Now if you want to find out the average value, so the average value I naught is equal to 1 by 2 pi integral theta 1 to pi minus theta 1, because this is varying from this to this only, right? Theta 1 to pi minus theta 1. Vm sine of omega t minus E by R into d omega t. That's it. Now if you solve this equation, you will get 1 by 2 pi R 2 Vm cos theta 1 minus E into pi minus 2 theta 1. That's it. So now if you want to find out the RMS value of this particular waveform, IRMS, similar procedure, I am not changing any procedure, okay. IRMS square is equal to 1 by 2 pi integral theta 1 to pi minus theta 1 Vm sine of omega t minus E by R into d omega t. So this is completely whole square. So now you can, if you can try to solve this, and you can get approximately a value of 1 by 2 pi R square Vs square, or we can write that Vm square plus E square into pi minus 2 theta 1 plus Vm square sin 2 theta 1 minus 4 Vm into E into cos theta 1. So this whole thing will be IRMS square, okay. So if you want to find out IRMS, this will be under root. So that is that much simple. We know, I mean, like once you do this algebraic calculation, you will come to know. Further, what is the power delivered to the load? The amount of power delivered to load is the total voltage of this back EMF into current plus the load drop, that is RMS square, IRMS square into R. Now if you want to find out the supply power factor, input power factor, so we know that is power delivered to load to the source voltage into RMS value of current, IRMS. So that is simple, like E into I naught plus IRMS square into R divided by Vs into IRMS. So that is how we can easily take out the calculations from this. So that is how, I mean, any problem that will be related to this, you can easily solve. Now the same thing let us see with the help of our Matlab simulations. So in this one, let me put this is R, resistance is 10 ohms and amplitude is 10 volts and I want to see how the things are happening. See how nicely the figure is coming. So for further our analysis, what I'll do, I'll keep the resistance to be a little high so that we can see the waveform clearly. See, maybe I'll reduce the resistance to 1 ohms. So we can see one by one waveform how it is actually happening. So when it is switched on, the current started flowing through it, and then it stops, and then it is started. So you are able to see there is a gap that exists from the voltage. This is the source voltage, but this is the current. The yellow one is the current. So this is the gap that you may see clearly. Okay, that is how the current waveform only starts from theta 1 to this theta 1. So now because it is a very high voltage, so you will not able to see properly. I'll keep like it is like 80 volts, then you will see that waveform very clearly. Yeah, you can run for some more time. You can see that. You can see that. See, till this point the current has not started, and then from here the current has started and it has stopped here, that yellow line. So that blue line is your source voltage. Now this some sort of violet line is showing you the diode voltage. See, so you can from here also you can find out what is the peak inverse voltage of the diode. So if I take into the vertical axis, you can see 80 volts. Observe carefully, 80 volts. Whatever we kept, same thing. So this one will observe. This should be 180 volts. So it's clear. So from this analysis, we can clearly say that whatever the theoretical analysis that we have did, it is quite applicable to this kind of applications.